Welcome, everyone, and hello, good evening, good morning, good afternoon. I am delighted to introduce our keynote speaker now, Nicolas Papernot. Nicolas is an assistant professor. Gleich. Nicolas is an assistant professor in the Department of Electrical and Computer Engineering and the Department of Computer Science at the University of Toronto. He's also a faculty member at the Vector Institute, where he holds a Canada CIFAR chair and a faculty affiliate at the Schwarz-Reisman Institute. His research interests span the security and privacy of machine learning. Nicolas is a CONAV researcher and was previously a Google PhD fellow. His work on differentially private machine learning received the Base Paper Award at ICLR 2017. He is an associate chair of IEEE Security and Privacy Auckland and an area chair at ISB. He earned his PhD at the Pennsylvania State University working with Professor Patrick McDaniel. Upon graduating, he spent a year as a research scientist at Google Brain. Now, Nicolas Papernot actually has one of the first papers on security in deep neural networks, where he showed limitations of deep learning in adversarial settings. He did seminal works on attacks against machine learning and adversarial machine learning, and his papers are widely cited. So it's great to have you today with us. Nicolas will talk about increasing trust in machine learning through governance. And the brief abstract is the attack surface of machine learning is large. Training data can be poisoned, predictions manipulated using adversarial examples, models exploited to reveal sensitive information contained in training data. This is in large parts due to the absence of security and privacy considerations in the design of machine learning algorithms. Designing secure machine learning requires that we have a solid understanding as to what we expect legitimate model behavior to look like. We illustrate these directions with recent work on adversarial machine learning, model stealing, privacy-preserving ML, machine unlearning, and proof of learning. Nicolas, it's great to have you here again. Sorry for the distractions, and the stage is yours.
Thank you very much. Hi, I really appreciate the kind introduction. I'm very excited to be here today. And I'm going to talk, as Haya mentioned, about our recent work on understanding what it means to achieve machine learning governance by increasing trust in machine learning systems. Before I start, I'd like to mention that this is work that I did in collaboration with a lot of researchers and in particular with my students. So I try to indicate the authors of the different projects that I'm discussing at the bottom of the slides to give them due credit. So to get us started, I wanted to first understand what is the scope of the talk. And so the first aspect that I'm going to discuss a lot today, of course, given the conference, is security. And so if we look at security in the context of machine learning systems, we can see that there are attacks that are spread out across the typical attack surface that we observe in computer systems with the confidentiality, integrity, availability triad. If we look at confidentiality itself, it can be with respect to both the data that is being manipulated within the machine learning system, but also it can be the confidentiality of the system itself. And I'll spend a little bit of the talk discussing model stealing attacks in particular, where adversaries might attempt to steal the intellectual property that the model represents. In the middle of the slide here, I have a recent example of work on training data reordering from my postdoc, Ilya Shumailov, who basically demonstrated that we can not only perturb the behavior of training algorithms by inserting poisoned data, but we can also achieve the same effect, this corruption of the training set, simply by reordering the points that the machine learning system is analyzing during training. And so this really intriguing result shows that essentially the generalization guarantees that machine learning systems rely on, they depend on the stochasticity of the training algorithm. And so as soon as the adversary is able to manipulate this fundamental assumption to machine learning, they can basically arbitrarily corrupt the behavior of the training algorithm, and in particular, its integrity. Finally, the last component of security is typically availability. And so here, again, machine learning systems are not an exception, and they're also vulnerable to availability attacks. In particular, what we were able to demonstrate is that we can find inputs to a machine learning system that will maximize the latency of its predictions. And so what this means is that machine learning systems are relying on heuristics to improve the efficiency of computations that are involved when making predictions with machine learning systems. And so the hardware that is used to accelerate the machine learning software relies on these heuristics to make these computations more efficient. In particular, there is a lot of sparsity in the computations that deep neural networks make. And so if we look at the inputs themselves to these systems, we can craft malicious inputs that are designed to essentially ensure that the computations on these inputs will not exhibit any sparsity. And this, as a result, increases the time that it takes for the machine learning system to infer and to predict on these inputs. And so you can imagine that if you're deploying a machine learning system on a mobile device with limited battery, or in a data center at a scale where the energy footprint is significant, then this form of availability attack can turn essentially into a denial of service for the machine learning application. The second aspect that I'm going to discuss in the presentation is around privacy. Here, the question is a little different, where we're using machine learning systems to analyze data that is sensitive. This is very often the case in healthcare. And what is going on is that we have to be concerned about the possibility that the machine learning models that we are training from these sensitive pieces of data are going to memorize some of the information contained in the training data. And so an example of why this is concerning is work by one of my students, Christopher, who demonstrated that it is possible to tell whether or not a specific machine learning model trained on a specific piece of data simply by having the ability to query the model on inputs that the adversary chooses. And so what this means is, for instance, if I trained a model to predict whether a patient is going to be readmitted to a hospital or not, then I can tell whether the data corresponding to a particular person was used or not to train this model, which obviously can leak private information about this person. And so in the second part of the talk, I'll explain how we can provide guarantees of privacy when training machine learning models. And then finally, the last aspect that I wanted to mention today while setting up the stage for the presentation is the ethical implications of machine learning. So there has been a lot of attention given recently to the limitations of machine learning, for instance, for facial recognition, which does not perform as well on all its test inputs. There has also been a lot of work around deepfakes and how machine learning models facilitate the process of creating deepfakes. And so the broader question that I'm asking today in the talk is, in general, how we can ensure that users that interact with deployments of machine learning can trust that the machine learning model is aligned with our norms as humans, our human norms for what society should look like if we want to have a responsible application of AI. And so this is a problem that is inherently tied to a lot of the work that has been done in the computer security community. I pulled this quote from 2004 from Butler Lamson, who stated that practical security has to balance the cost of protection with the risk of loss. And so the risk of loss is the cost of recovering from the loss times its probability. And here, when we think about machine learning, this is no different. We are now getting evidence that machine learning is able to bring us benefits as a society, but also comes with its own risks. And so we have to learn how to effectively balance these risks with the benefits. And so what I discussed today in this talk is a set of techniques which are going to standardize the interaction between the different principles that are involved in the deployment of machine learning. So that is the end users, the companies, the organizations, the hospitals, and the regulators, with the overall aim of ensuring a responsible application of machine learning, which is one that is beneficial to society. And so the first component to achieving machine learning governance, and this is a thought process that we've described in a recent preprint here that I put the title of at the bottom of the screen. Really, the first component of this line of thought is to say, well, if we want to standardize these interactions between different principles, we have to know who are the principles. And so there's this need in machine learning systems to establish identity, a notion of identity, which is fairly sort of foundational in traditional computer systems. But in machine learning systems, we haven't yet developed a very crisp notion of what the identity of the principles involved in this machine learning systems are. And to give two examples, I'm going to discuss the concepts of data and model ownership. So who owns the data that the machine learning system is processing, who owns the model, and how to prove that. And so why this is challenging? Well, because the progress that machine learning research has made in learning with little to no supervision makes it easier and easier to steal machine learning models. What I mean by this is that simply by having the ability to observe the predictions of a model, an adversary is able to essentially reproduce and create a copy of that model. The reason is that you can treat the predictions of the model as essentially labeled data that you can use to then train your own model that performs similarly on the same task. And so in machine learning research, there has been a lot of progress around something called semi-supervised learning, where only partially labeled data is available. And what this means is that when an adversary is trying to steal a machine learning model, they now need to make much less queries on inputs and observe the predictions of the model on these inputs before they are able to reproduce the model to a sufficiently high degree of accuracy. And so this is sort of a pessimistic setup that I'm putting here, because what this is implying is there is really not much we can do to prevent model stealing, because it's fundamental. The reason why we can train machine learning models from data sets is the reason why we can also steal machine learning models simply by observing the predictions they make. And in fact, we've made so much progress in understanding how to steal machine learning models that we can now do this without having any access to realistic training data for the model. So typically what we would do is we would have unlabeled data, and then we would have the model that we're trying to steal label that data so that we can steal the model. Now what we have realized is that we can use generative models. So you may have heard of generative adversarial networks, GANs, which have been discussed a lot, for instance, in the context of deepfakes, because they're able to produce very realistic images. What we're doing here is we're training a generative model to tell us what are the queries that we should ask the victim model to learn as much as we can from the victim model's decision boundaries. And so what we have here is we have a generator that takes in random noise and then outputs an input that is essentially a synthetic input, which could have been from the distribution, for instance, from which the training set is sampled. And then we're going to send this synthetic input to both the victim model that we're trying to steal and the stolen copy that we're trying to reproduce on our local machine. And then we're going to compare the predictions of these two models, the victim model and our copy of it, and define a loss, which is essentially characterizing how far these predictions are. And then we're going to take this error signal and propagate it back all the way to the generator, which means that we're going to help the generator generate inputs here, synthetic inputs, that maximize how different our stolen copies predictions are from the victim model. And why this is interesting? Well, because once we have these synthetic inputs, we can ask the victim model to label them. and that will give us more information on how to train our copy of the model in a way that it will now match these predictions of the victim model, because we've found good examples of where our stolen copy was not a good approximation of the victim model. And so why this is important is it's because it means that we're now effectively able to steal machine learning models with absolutely no prior information about how they were trained. And so this is really concerning for the intellectual property of models that are deployed, for instance, on the internet through APIs that can be easily queried. And so, as I said, model stealing is very difficult to prevent, because if you don't reveal the prediction of your model, you basically also harm the legitimate users that are trying to use your model for a legitimate purpose. And so here, what we did in this piece of work called dataset inference is we flipped the problem around to give an asymmetric advantage to the defender by thinking about model stealing as essentially the idea of stealing the knowledge that is in the victim model. What this means is that when an adversary is trying to steal a copy of a model, they're essentially trying to steal information that is contained in the model's training set. And so if I, as a model owner, suspect that someone has stolen my model, then what this means is that their stolen copy should contain information that was originally in my training set. And this gives me an asymmetric advantage as the model owner, because I have access to the training set that I used to create my model. And so what this means is that I can take this training set and go and inspect models that I think have stolen, are basically stolen copies of my model. And I can look at how they predict on this training set to tell whether or not they are indeed stolen copies of my model. And so this is exactly what we're doing here. And we're actually using a privacy attack to do that, called membership inference, which I described in the first slide where I introduced privacy. We're basically taking the victim model's training set and taking a few points from it, and then sending those to the potentially stolen copy. And then we look at whether the stolen copy's predictions allow us to infer whether or not this point was used as a training point for this stolen copy. And if the adversary has successfully stolen our model, then essentially the stolen copy will be more likely to predict with high confidence, essentially, on our training points. And so we can recognize by submitting enough of our training points to the stolen copy that it is indeed a stolen copy. And so this is an interesting setup, because we're taking an attack and using it as a defense. But here, whereas the attack would have been difficult to achieve on individual training points, because the defender has access to the entire training set, they are always guaranteed to be able to tell whether a model is a stolen copy or not, because they can aggregate the signal across multiple of the training points. So this is one way to defend against model stealing. And what's interesting about this approach, in my opinion, is that it really shows us that perhaps model ownership is not very different from data ownership. And this is an interesting question, because there's a lot of conversations currently, especially in the legal community, in defining what it means to own a machine learning system. And in this work, what we're basically showing is that really owning a machine learning system is not very different than owning the data that was used to train that machine learning system. The second approach that I wanted to cover is ownership resolution through proof of learning. And here the idea is to say, well, how can I demonstrate that I trained a specific machine learning model proactively? Well, what we observed is that training algorithms that are used, for instance, in deep learning, generate secret information organically as we run them, because they are stochastic. And so what it means is that someone training a model has access to secret information that someone trying to steal the model would not have access to. because the person that is training the model has access to all the intermediate states of the training algorithm. And so this is precisely what we're proposing here, is to say, if I, as a model owner, want to proactively protect the intellectual property of the model that I will obtain at the end of the training procedure, then I can record all of these intermediate states achieved during training and use that to build a proof that I can essentially register with a third party, for instance, to essentially obtain the equivalent of a copyright for this specific model. And so the way that it works here is if you take a training algorithm like stochastic gradient descent, which is basically minimizing the error of the model by taking gradients of this error with respect to the model's parameters, then at each iteration here, we're going to obtain a new set of model parameters. And so in the proof of learning, we're going to record not only these individual model states, but also enough information to reproduce all of the stochasticity of the training algorithm afterwards. And so what this means is that, in particular, we're going to look at hyperparameters of the procedure, but also the data itself that was used to obtain that particular model update. And then what that means afterwards is that a regulator that would like to, for instance, verify that we indeed submitted a valid proof of learning can inspect these individual model updates and reproduce them. And if the regulator's reproduction is sufficiently close from the one that the model update that was contained in the proof of learning, then the proof of learning is deemed to be valid. And so here, this is essentially all of the information that we have to include in the proof of learning. As I said, the weights, the data that was selected, which we can hash if we prefer, to basically ensure that we commit to these specific data points. And then the auxiliary information, which is just hyperparameters of the training procedure. What will then happen when the regulator wants to verify this proof of learning, they're going to start by looking at the first state of the weights, and they're going to verify that this is indeed initialized from a random state. And so using some statistical testing, you can basically ensure that indeed the proof of learning started from an initial state that was sampled randomly. And then the regulator is going to look at each of these individual model updates, and rather than verify the entire sequence in one shot, which would not be possible due to the error in the reproduction that would accumulate across the different model updates, we're going to instead have a verification that is stepwise. So we're going to take some of these pairs of model states, and we're going to verify individually these specific model updates and ensure that if we reproduce them with the information contained in the proof of learning, then we are able to get the same weight in the next step. And one way to make this process more efficient for the regulator and to avoid repeating the entire training run is to select carefully the updates that are verified. And one approach that we found for doing that is to select the largest updates. And this has advantages in the sense that it makes it more difficult for an adversary to forge a proof of learning that would pass the verification but be an illegal proof of learning. And so this is basically the gist of our security analysis, where we looked at this proof of learning proposal, and we essentially attempted as an adversary to find ways to obtain a proof of learning sequence that would pass the verification, but would have been obtained at a smaller cost than the cost faced to train the model initially. And what we found is that no matter how we tried to spoof these proofs of learning, essentially there would be a discrepancy at the verification stage, either, as I just explained, because the model update would be too large, and so it would be detected in our verification that is sorting updates by the magnitude of the updates, or because we found that simply reversing the process of gradient descent, so trying to find the inverse of gradient descent, is just computationally very intense. And so it is at least as expensive as training the model. And you can understand this by thinking about how stochastic gradient descent works. When you want to invert stochastic gradient descent, you need to do at least the same amount of effort than someone that is performing gradient descent in the first place. And so it's not possible to spoof this without paying the same computational costs than you would have paid by training the model. And so this is the first part of my presentation where I hope I give you a good understanding of why it's challenging to have a concept of identity in machine learning and how we can use techniques like dataset inference or proof of learning to understand what is secret about the training procedure and that the model owner can produce when challenging someone that may have stolen their model. Okay, and so this means that now we have a good understanding of how we could possibly identify entities that are the owners of a machine learning model. And so now this basically serves as the foundation for holding these principles accountable for the failures of the machine learning model. And so there are a couple of directions. This is very much an open research area. So here I just wanted to state some problems that I think are interesting to work on. The first one is that if you look at the proof of learning proposal, essentially it allows us to verify the integrity of the training procedure. If I'm given a proof of learning, I can verify that the model owner has trained their model and that the training algorithm's integrity was indeed guaranteed. Now, the question is, can I use similar approaches to prove other guarantees that would essentially give me more trust in the machine learning system? You could think about things like fairness, for instance. Another approach that we can hold not the model owners accountable, but the model users, is to think about what is useful to log in a machine learning system at inference. And so in particular, in the work that I'm going to discuss in the next part of the presentation, I'm going to discuss attacks against privacy that work by essentially querying a model on data that is very similar to its training data. And so you can imagine that if you had proper logging of queries that are submitted to a model, you could notice the difference between here, what I have on the left, and here, what I have drawn on the right, where a normal user would essentially, each of these boxes are points from the data input space. If here my red point here is my training point, a normal user would just sort of randomly sample from the distribution and submit these queries. But an adversary is going to submit queries that are all very close from the training point, because that's how you're going to validate the privacy property. And so I think that by logging data at inference, we should be able to devise mechanisms to defend against these attacks. And I think this is very consistent with search engines or email, where we have very poor authentication. And so logging, auditing is very important to achieve security there. I think when we look at machine learning APIs, we have similar issues that could be resolved. I'm going to skip this slide here in the interest of time. So the next part of the presentation, once we know who the model owners are, once we know how to hold model owners and users accountable, we also want to prevent failures from happening, which is sort of the next phase of achieving machine learning governance. And so here we want techniques that provide guarantees of security or of privacy, guarantees that we can verify. And so here, I think the best example in the machine learning literature is the one of privacy, where there has been significant progress made in how to obtain privacy in a machine learning system. So here to start, it's important to define what privacy is. And so privacy is a very subjective notion. If you talk to your colleagues, to your friends, they will give you very different definitions. In the privacy community, we've agreed on differential privacy being sort of the standard way of formalizing what it means for an algorithm to be private. The idea is to say that if an adversary is observing the outputs of the algorithm, it shouldn't be able to tell whether the algorithm was operating on this first data set here that contains the user's data, or this second data set here that does not contain that same user's data. And so what this means is the adversary is not even able to tell whether that specific user contributed their data or not to our algorithm. And if we prove this for all possible pairs of data sets that only differ by one training record, then we can prove for any users that they haven't overly influenced the outcomes of the algorithm. And of course, we have to, this guarantee is never going to be perfect. It's a statistical guarantee so that we're still able to learn a little bit from the data. And the way that we quantify this is by comparing the probability of the algorithm making specific outputs. And we make sure that these probabilities here on the left are very close on the first data set than they are to the right here on the second data set. And how close they are is parameterized by this parameter called epsilon. When you look at papers on differential privacy, you'll see that the main result is often to show how small the value of epsilon here is, because the smaller the value is, the stronger the privacy guarantee is, because the more indistinguishable these two settings are. So how do we obtain privacy in machine learning? There are several approaches. I'm going to present one here called PATE. I did not come up with the name, even though this might be surprising because I'm French, but the acronym stands for Private Aggregation of Teacher Ensembles. And I'm going to present it because it allows us to understand why privacy is such a, differential privacy is such a good definition of privacy when it comes to training machine learning models. And so the idea is to say, well, we have one sensitive data set. We're going to partition it in n subsets of data, which are mathematical partitions in the sense that they don't overlap. Then from each of these partitions, we train one machine learning model. Here, we don't have to do anything specific about how we train these models. The only constraint is that they're each trained only from one partition. So we have n models that are all performing the same task, but they have all been trained from different data sets. Then we take these models and we ask ourselves, how do we have them predict while protecting privacy? And the way that we're going to do this naively is we could say, I'm going to take my input that I want the models to predict on, submit it to the individual teachers, ask them to vote for a prediction, then I'll output the prediction that received the most number of votes. While that is a reasonable approach, it doesn't always provide privacy. It does provide an intuitive notion of privacy when you think about it, because when all of the teachers agree, it makes sense that this prediction was made several times independently. So it doesn't depend specifically on one of these partitions. So it doesn't depend on one of the data points that was included in the original data set. That said, if, for instance, half of the teachers agree on one point, on one prediction, and the other half agree on another prediction, you can see how one teacher changing their prediction can change the output of the aggregated prediction. And so here, to protect privacy and obtain differential privacy, we have to randomly sample noise and add that noise to the votes that the teachers submit. And this way we get the notion of indistinguishability that I presented in the previous slide defining differential privacy. And so the interesting thing is that every prediction that the teachers will respond to is going to slightly increase the privacy budget that we've consumed to answer the overall queries. This is because, remember, in the definition of differential privacy, we are bounding the privacy leakage. We're not making it zero. And so to bound the overall privacy budget and make sure that as we make more and more queries, we don't get an infinite budget, we're going to use this ensemble of models not to respond directly to user queries, but rather to train a student model that will take unlabeled data and have the teachers label this unlabeled data with privacy, so that we can transfer the knowledge that we've extracted with our teacher ensemble into a student model while protecting privacy. And once we've done that, we can take the student model and have it respond directly to user queries. And we don't have to query anymore the teachers. We can even delete them as well as the data. All we need is to keep this student model, and the total privacy cost is fixed. And so why this is interesting to understand how privacy, differential privacy, and the goals of machine learning are aligned is you can think about it this way. The more the teachers agree, the more consensus there is, the more likely that prediction is to be correct because it was made several times independently. But it also means that it is easier to output this prediction with strong privacy guarantees because we can insert more noise in the votes of the teachers before we change the label that received the most number of votes. And so there's this very rare alignment between the privacy guarantee and the goal of machine learning, which is to generalize well to new points. Another advantage of this particular approach is that it can easily be deployed in a distributed setting. So here, in the interest of time, I'm not going to cover the details, but the idea is to say, well, if I originally already had data that was partitioned, for instance, if multiple hospitals each locally had a partition of data, then I can combine this mechanism with cryptographic primitives to be able to do the inference procedure over distributed models, where essentially the data that I want to predict on is going to be encrypted and then sent to the individual teachers, which can process it using homomorphic machine learning. And then I'm going to use their predictions and aggregate them as done in Pate before I respond to the party that wanted to have this input labeled. And so this allows me to have both the guarantee of differential privacy and guarantees of confidentiality that I'm not leaking the models or the test inputs that I'm predicting on. So I think this is really a setup that can be very advantageous in decentralized machine learning, in particular because unlike federated learning, it allows all of the parties to retain their models locally and to have different models, in particular different model architectures, which is, I think, a strong advantage. Another advantage of differential privacy is that it's robust to any future attack that we may come up with. And so this is a very strong and very appealing security guarantee. It doesn't depend on the knowledge that the adversary has. And in particular, what we showed here is that differential privacy is the only way to train a privacy-preserving machine learning model that is robust to adaptive attacks against membership inference. So here, what we did in this piece of work is we took membership inference attacks, which very often rely on the confidence of the model, because the more confident a model is, the more likely it is that the point that you're querying it on was used to train the model. So some researchers have proposed to hide the confidence of the model as a way to make membership inference less likely to succeed. But what we showed in this work is that we can actually perform membership inference with only access to the labels that the model predicts. And so what this means is that we can, by design, break defenses that are relying on hiding the confidence of the model, because we now are no longer using the confidence information for attack. Instead, if we train the model with differential privacy, what we see in this graph is that it is the only approach that provides robustness to this new form of attack, despite the fact that the model was trained prior to knowing that this attack existed. And so this is a very appealing guarantee. To conclude here, I think the goal of assurance is really to align machine learning systems with human norms. And so what I've shown here is an example with differential privacy where we're able to align the training algorithm with what we as humans would call privacy. But what remains an open problem is to combine different human norms and achieve them simultaneously when training a model. And I'm going to come back to that very quickly just as I conclude the talk. But before, I want to talk about the last stage of model governance that I included in this presentation. which is really once you have a model that you can trust because you have this notion of assurance, how do you manage the model in particular as the model is deployed and as users start interacting with the model? And there is in particular two things that are interesting to think about is how we would patch machine learning systems. So we know how to patch software, but patching machine learning systems is something that we need to think more about. And when do we decide how to retire a machine learning system that we should no longer use? So I'm going to give an example for the first problem, which is patching. Here, when we think about patching a machine learning system, what we know how to do very efficiently is how to teach a machine learning model a new behavior. That's fairly straightforward because all we have to do is present it with new training data and continue the training run. The problem is that if we want to patch, sometimes we don't only want to add behavior, we might want to remove behavior. One example of this is for privacy reasons. For instance, in Europe, the GDPR framework introduces the right to be forgotten, which in machine learning is difficult to comprehend because we should assume that a machine learning model will memorize information contained in its training data. And so if one person requests to delete their piece of data from our data sets, then we have to essentially be concerned that we have to delete all of the models that we possibly trained on this data set. Another reason is that if for a security motivation, you realize that your data set contains malicious points, for instance, someone has poisoned your data set, then you might want to take a model that you trained and remove the effect of these poisoned points. And so to be able to do that, we have to achieve something that we call machine unlearning, where we want to essentially remove the influence of specific training points. And so here, differential privacy is not a good solution to that, because in differential privacy, we bound how much we learn from each training example, but we don't make that bound zero. And so this means that each training example still has a small, but still a little bit of influence on the model. Whereas here in machine unlearning, we want to make that influence zero, and we want to make it zero for very specific points. We don't want to guarantee that it's for any training point. We want for a few training examples. And why this is difficult, again, it comes back to the stochasticity of training algorithms and the fact that because the training algorithms are iterative and solve objectives that have multiple minima, it's very hard to take a model and its parameters and to understand how individual training points influence these different parameters. And so we can't just cancel out the effect of a training point by looking at the model's parameters. Instead, what we want to prove is something a little stronger, which is that the distribution of models that are training algorithm outputs once we learn from the data set that contains the point to be unlearned, and then unlearn the specific point that we want to unlearn, the distribution of models we obtain should be the same than if we had run our training algorithm without the point to be unlearned in the first place. Because then if we are able to prove that, it means that we obtained a model by learning then unlearning that we could have obtained without learning in the first place from that point. And so one naive way to obtain this guarantee is to say, well, when I get a request to delete a data point, I'm simply going to delete my model and then retrain from scratch. But of course, this is going to be very expensive. So one approach that we propose to make this more efficient is to look at the training set and similar to Pâté, to begin by partitioning the data set. Why this is interesting in the context of machine unlearning is that now if I have a request to unlearn a specific piece of data, then I know that this specific piece of data is in only one of the partitions here. So for instance, this red piece of data. And so when I need to retrain the model from scratch, here, retraining the model from scratch from on this small partition only will be faster than retraining a model that would have been trained on the entire data set. So that's the first simple improvement. The second improvement we introduced is this notion of slicing, where you can see that each of these partitions is further divided in slices. And what this is useful for is when we look at the training algorithm, typically when we train something like a deep neural network, we analyze the entire data set in each of the epochs of training. What this means is that we run our training algorithm multiple times on the entire data set. Instead, what we propose here is to say, well, why don't we start the training algorithm on only, for instance, 10% of the data, and then save the model parameter states after we've completed these 10% of the data. And what this means is that we can now introduce another slice of data. So let's say we're now training on 20% of the data, train for a little longer, save the model parameter states again, and then introduce yet another slice of data and so on until we've analyzed the entire data set. And then we have a collection of intermediate model states. And we can, when an unlearning request arrives, we can identify the last model state that was achieved before we started analyzing the point that needs to be unlearned. And we can revert the training algorithm to that state and resume training from that state, which will be faster than if we had to resume training from the initial state of learning. And so by combining both the sharding and the slicing operations, we're basically able to make it faster to retrain a model to remove completely the effect that a training point had on the model in the first place. So this is basically what I wanted to cover today. To conclude, again, I'm going to remind you that I think at training time, what we need to think about is assurance, where we want to ensure that the model is aligned with our human norms. So I've discussed privacy, but of course, there is more progress to be made in obtaining things like integrity or fairness. One challenge on this, on the way to achieving this form of machine learning governance is the one that I mentioned very briefly a little earlier, which is to achieve multiple forms of guarantees when there is an interplay of risk. One very good example of this is privacy and fairness. So I'm just going to show you one last example, where here we looked at medical data sets, and we found that it is hard to achieve privacy and fairness simultaneously on these data sets. And to understand why, if you think about it, in medical data sets, the interesting patients to learn from are in the tail of the distribution, because you have very few examples of patients that are sick, fortunately, I should say. And so when you try to achieve privacy, you're going to run your training algorithm in a way that prevents it from learning from the tail of the distribution. So this is not only going to impact your accuracy, but also your fairness, because if you want to have good performance on the subpopulations that are, for instance, the less represented in the data set, then you're basically asking for the opposite than what differential privacy is asking you. You want to learn from the tail of the distribution. And so on one hand, you are preventing your algorithm from learning from the tail of the distribution. And on the other hand, you want it to learn from the tail of the distribution. So there's some inherent tension here, where it's not possible to achieve the privacy and the fairness objectives at the same time. And so this is fairly fundamental, and I think it requires that we rethink sort of either the definitions of what it means to be private or fair, or we have to decide as a society, how do we trade off these two properties and which one we favor in regard of the other property, which is something that I don't have a good answer to. And then to conclude, I will say that another limitation that I very often encounter in my area of research is the lack of alignment with legal frameworks. And a very good example of this is in privacy, where machine unlearning is very well aligned with legal frameworks that introduce the notion of the right to be forgotten. But if you look at differential privacy, most of the frameworks for regulations rely on the concept of anonymization. So data is deemed to be private when it has been properly anonymized. But in the computer science research, we know that anonymization does not work. It has been proven many years ago. And so now we've moved beyond that, and we reason about privacy at the level of algorithms rather than data. And so there's this complete mismatch between what the computer science community is developing and what the regulations are asking for. So you can ask yourself, how are we going to ensure that this technology has an implication to the real world if the legal frameworks are not aligned with the technology? Okay, and so this is the conclusion of my talk. I want to finish on an optimistic note, because as security researchers, we often come in the room and ask people to give us a little bit of the performance of their systems so we can provide them with security. And here, I think in machine learning, it's a little different, because the reasons that machine learning models are not trustworthy or are not secure is often very well aligned with the underlying problems that the machine learning community is trying to solve, and in particular, the ability to be able to train a machine learning model that generalizes well. And so I think that by looking at the trustworthy aspects of machine learning systems, we're actually informing the machine learning community as to how to better design training algorithms that generalize well, which is the goal of the machine learning community. So this is a very nice area to be working in terms of the potential of the interdisciplinary results. And then I'll finish with some photos of my students who contributed to this work. And I'd like to acknowledge all of the inputs that they've put into the work that I presented today. Thank you, and I'll be happy to take questions.
Okay, Nicolas, thank you for this very exciting, open-minded, mind-broadening talk. Are there questions from the audience? Okay, if not, I have a lot of questions, but I'll start with one, which is very naive. So when you presented your approach to detect if somebody has stolen your model, this approach is based that you make a query with your training data set and get the reply. But my question is the following: if you do so, wouldn't the party which has stolen your model also now steal your data? Because now they can only log all your queries, and now they also have your data.
Yes, that's an excellent question. And this is something that we were taking into account when designing the approach. And so something that I didn't have time to go into the details of is that the amount of training data that you have to reveal is very small. So for instance, when we train a model with in the order of 50 or 60,000 points, we were able to prove with very high confidence, above sort of 99% confidence, that it is a stolen model, with essentially revealing about 30 of our training points to the stolen model. So it's a very small fraction of the data set that we're using to be able to infer whether the model was stolen. And the reason is that essentially, when you look at the underlying attack, the membership inference attack, you can think of it as it has 50% chance of succeeding, because the underlying rate is, if you guess randomly, you would have a 50% chance of guessing correctly. And so on each point, the membership inference has a slight advantage. It's a little bit better than random guessing. But then we just use multiple training points to basically increase our confidence sufficiently up to a point where we know that the model was stolen. But essentially, the number of points you reveal reflects how confident you are that the model is a stolen copy of your model. Yeah.
Thank you. Other questions? Okay, so I can ask another question since, okay. So I liked a lot, you made a very good point about who is the owner of a machine learning model. This is a tricky question because in a way, all the AI algorithms are open source. So basically, then the question is probably who has the data, basically is the owner of the model obtained from this data. But in a way, you said that basically, owning the model is equal to owning the data, right? But what about models which are hybrid between symbolic knowledge and statistical knowledge? Because basically all the models you are talking are statistical, are not symbolic models, if you wish. But now there are these ideas of combining with symbolic knowledge, which can be logic programming, other techniques. In that case, there is this other source of knowledge, which then you cannot say that owning the model is equal to owning the data, right? Do you have any comment on this?
No, I think that's absolutely right. And I think just to, I guess, moderate my claim is that I think what we came to the realization after completing that project is that it may be the case that it's hard to distinguish model ownership from data ownership.
Yeah.
And so the reason is that then you have to argue about the complexity of the algorithm that you're using to basically either train or do the inference. And this is something, I guess, that comes more to sort of a legal discussion. I was actually having some conversations with lawyers, and there is this notion of how much complexity the algorithm has in when it comes to post-processing the data and to basically be able to differentiate the data from the models. But I think technically speaking, it is a little harder to measure this complexity. This is something we try to do with the proof of learning, where we're basically measuring, we can, if we look at the proof, it gives us a rough indication of how much computational power went into the training of the model. But then judging what is a complex versus not a complex algorithm is something that we haven't looked into. And I agree with you that it would be an important distinction between sort of model ownership and data ownership if there were to be one.
But I feel, to be honest, that this is not only a problem of machine learning model. Today,
oh, absolutely.
People can reverse engineering everything. So we could extract using automata learning the implementation from mobile phone without having access to the code of certain protocols. So this will be a general problem. But I feel, on the other hand, that if you have general models like the big pre-trained networks, then those don't need to be protected. I mean, they really are in the open, right? Because they are done in this way, and transfer learning, you can adapt them to your own application. But the models which are very specialized, are really the ones where probably companies make a lot of money, I'm sure there will be legal agreement, there will be more care about protecting the model. I don't think they will be just exposed to anyone. And so I'm not sure whether this is really such a critical problem always, if you wish.
I think it's basically a problem if, there is part of it that needs to be addressed legally, where you're basically putting agreements on how you use the software. But I think it is a problem in the cases where the models are exposed publicly. So there is a lot of applications where you can just query the model by submitting a query on a server, or you could imagine someone is trying to reverse engineer the model. And so that could be useful to then later attack it. It could be a reconnaissance step. So for instance, in a few years ago, I did a lot of work on adversarial examples where the first step of finding an adversarial example was to recover an approximation of the model simply by interacting with it. And there, the motivation is not necessarily intellectual property, it's just that you're gaining information, you're doing reconnaissance, and then afterwards you can perform the attack as if you were in a white box threat model. But I will say that in my conversations with industry, I do feel like the intellectual property question comes back a lot. So there is at least some interest in what are the different ways that one can protect the models that they've trained.
Yeah, that's a good point. It would be interesting because my impression was that the very sophisticated models are used internally, not even exposed to web. So
Yeah.
I wonder whether there are a lot of companies just, because if I train a model to recognize chemical substances, and then I put this on the web and everyone can pay a little money using my model, I'm not sure those cases will happen a lot, to be honest, especially when you don't have a lot of data available for training, which is the other issue.
Right. I think basically here there are two things. Is now we can do these attacks without having access to the training data. And then the second aspect is that a lot of times now models are being pushed to the edge devices because the inference is just accumulating to such a large cost at the level of the provider. So there's a lot of work on compressing machine learning models to then deploy them on mobile phones, IoT devices, and so on. And there they become a lot easier to query. So I think that's one of the concerns that people have expressed to me.
That's great. Yeah, it's a very interesting point. So are there questions from the audience?
I think I see one in the chat, which is asking how should we combine the modification of the learning algorithms with different goals like privacy, security, and ethics all at the same time. So this is essentially the point that I was making at the very end of the conversation, where currently most research will study each of these individually speaking. And I don't think we have a good understanding, to be honest, of how to trade off these different guarantees. There is some sort of game theoretic way of thinking about it, where you have the user, you have the model owner, and they're all trying to trade off different objectives that are sort of weighted sums of the different properties that you might care about. But I don't think we have a good understanding of what the impact on performance of the models is. It could be that in some cases it's very aligned, the guarantees that you're trying to achieve, but in the case that I showed, the privacy and fairness, it can be sort of in tension. And so there is definitely more work that is needed there to be able to provide a good answer to that question.
Oh, there was another question. Can you see this question?
I cannot. I only
yeah, a different aspect of trust. Okay.
Oh, I think I just saw it. Yes.
Yeah.
So this is asking about physical deployments of machine learning. So with the examples of autonomous cars, for instance, I guess, how do we increase the trust in these resource constrained systems? So there, I should say that I don't think there's that much work to understand this. There has been work looking at whether, for instance, adversarial examples are physically realizable or not. And I think there, the answer is yes. And the other relevant work that I can think of is the sponge examples, where we were basically motivated by these physical deployments of machine learning, where you might have essentially a battery constraint device. And so being able to drain the battery of the model with something like sponge examples that I introduced on the very first slide of the presentation is concerning to the availability of the system. As far as preventing these forms of attacks, I think there is very little work in understanding that. And in particular, most of the research in the community focuses on the model itself in the machine learning pipeline and does not take into account the pre-processing and post-processing steps. It's not always the case, but I would say most of the time we are focusing on the model. And so it's hard to extrapolate from the results that we have in the publications to the consequences for these physical systems, where there is a lot of work that is needed to understand how the pre-processing impacts the performance. In particular, we've recently looked at things like keyword spotting and voice assistance. And so there, it's quite interesting that you can constrain the attacker's surface by looking at the pre-processing and in particular, how you capture the audio before you essentially process it with the machine learning model. And so we found that by looking at properties, signal processing properties, you can essentially decrease the attack surface that the adversary has access to before you even consider the model. So I think that's definitely one direction that we're curious about, and I'd be happy to send you a pointer to the paper after the talk.
We have one last question. If
Sure.
Nicolas, you can have a quick reply because we have to close the session.
Yeah, someone is asking whether it would make more sense to check whether data was legitimately used rather than whether a model was stolen or not. And I think this is a very good question that comes back at how you would test that someone has unlearned your data, for instance. There has been a little bit of work on how to do this through forms of poisoning. But I think this is something that is hard to appreciate at the moment because we have a hard time capturing the influence of training points on model predictions. And so making that mapping is rather difficult, but I'm happy to send pointers if you shoot me an email. I have a couple of papers in mind.
Okay, thanks. This was an excellent talk, and thank you a lot, Nicolas. I really appreciated your sharing your research directions, idea, and results.
Thank you so much, Elisa and Haya, for inviting me. Very happy to give this talk.
Yeah.
Thank you very much, Nicolas. It was a very interesting talk. Sorry, I had a few distractions, but it was very, very interesting.
Thank you so much.